You're on.
Alright. Hello everybody, my name is Zac Blanchard. Today I'll be showing you the Growinator. It's a hydroponic setup for your household. This is a pretty rough idea of what it'll look like. Mine's actually going to be about cut in half here because it's going to be going up against the wall. And obviously this picture is showing an outdoor setup. Have some wonderful reviews of it already. If you could flip the slide here. So you might want to know what hydroponics is. Hydroponics is a soilless growing operation. Most of the time when you're growing plants, you're going to be growing in dirt, which is usually has nutrients already in the soil. There's different forms of microbes, things that help the plants. So these are a couple of examples of soilless growing. Up here we have some cocoa, which is ground up coconut husks. There's some expanded clay balls and rock wool, which is basically just insulation. It's a little bit tighter packed. This allows for some moisture to be retained and also plenty of drainage because we are going to be cycling water through this quite a bit. I put up a couple different examples of various forms of hydroponics. So this would be what's called continuous flow. So there's actually water that flows through the lower parts of these pipes continuously. It's constantly being cycled up. The form that I chose is going to be a takeoff of this, which we're going to try and actually limit how much flow is going through to save some power. Another form is aeroponics, which is actually just another reservoir where the roots are being misted continuously. This allows for a lot of air movement to get to the roots and also moisture for them to absorb any nutrients they may need. And then there's flood and drain, which is basically a big table where you flood it and drain it several times a day. Lighting for plants. So over here we have a nice graph. The red would be what the sun's producing. This purple curve is the optimal absorption rate for plants. And then these lines here show you the various forms of chlorophyll. Over on the blue spectrum is the only place where plants get their form beta carotene. And then over here we get a very steep climb in chlorophyll synthesis. Basically, the blues are critical to vibrant growth. That's where you're going to get a lot of upward movement from the plants. That's where they're producing new leaves. So this will be optimal for growing things like lettuce, things where you're eating primarily the leaves and not the flowers. Reds are primarily where flowers are formed, so any thing that's fruiting. So things like tomatoes, cucumbers, things along those lines that require flowers and pollination, we're going to need reds being involved for that. And just touching on this briefly, nutrients are basically how the plants get their food. For this, we're not going to be primarily concerned with that because I don't have any sort of regulation for it, but there's three basic things that plants are going to want: nitrogen for the foliage, phosphorus for roots, potassium for healthy growth. There's some miscellaneous minerals like calcium that's going to be needed, and then for hydroponic we need to watch the pH level. So the idea was to design a self-functioning hydroponic system with a proper light spectrum. It'll self-water itself when needed, and size so that it'll fit somewhere indoors, because I'd like to be able to use this in an apartment setting so that I don't need to be purchasing food. This is an overview of the system itself. So we'll start with the power supply. We need a couple different regulators. 5 volts is going to be going up to the microcontroller and then to the sensors to power all the sensors that are going to be watching the moisture levels. 12 volts to power the pumps. And then we're going to want a constant current source for our LEDs that are up turn the lights on and off, the pumps on and off, and it'll be doing that by checking the moisture levels in the plants themselves. The water system, we'll be using PVC tubing that's gravity fed. This was a great example of that, so that the pump will actually bring it up. I'm going to be using a top fed system, so it'll be coming down into each plant individually. This will hopefully make it so I don't have to use a continuous flow and just be able to keep the medium that it's growing in moist. The pumps themselves, a couple things that were of concern would have been the static lift of them. The one that I chose has 3 meters, so that should be more than adequate to get up to a height requirement for the top tube. And then, of course, the flow of the pump, because, you know, if it's just a trickle, then, you know, it won't be getting enough moisture and water and nutrients, food to the plants themselves. These are the sensors. I passed one around if you wanted to take a look at it. It's going to function nicely with the micro we have because of the 3 to 5 volt in. There's actually 2 choices on the pin assignments, so I can use it as a digital and just get a high-low out of it. That has a trim pot right here. It uses a basic comparator system, and then an analog out, which there is 2 LEDs, so I assume the 4.2 is due to the drop in that if you're running it at 5 volts. And basically that's going to be able to check the moisture level, because the water that we're using is going to have a lot of salts in it due to the nutrient content. So, you know, the more moisture it's in there, it's going to provide an easier path for it. Thus, it'll drop the voltage down when it's wet, and it'll be higher when it's dry. These were some tests that I did with the sensors. So it functioned very nicely dry. It gave me the same value out every single time. I'm using the analog just for accuracy, and then using the ADC converter on the micro to convert it to a 12-bit range. And you can see that putting it straight into water compared to just some moist soil and compared to completely dry gives us a really nice range. So there was not a need to amplify the signal coming into the microcontroller. And then I'll be using these values to determine the moisture level. They were fairly consistent. There was one oddball out, so there may be a need to calibrate each sensor individually, which is fairly easy to do. There's only going to be 9 sensors, so getting a good range on each one individually and then tailoring the programming specific to those sensors will be fairly easy to do. The lighting system, this is the light that I built. I'm using some Gree LEDs. These are high-powered LEDs. They're 3 watts. They can handle up to an amp going into them. You can see the forward voltage to the entire array is a little bit off, which could be a little concerning with LEDs, but each LED array is going to have its own buck converters, so that difference won't matter because they're each being powered individually. Another big concern was a heat sink, so I needed a large heat sink because, as we'll see later, the red LEDs drop off very quickly in terms of light output, depending on how hot they get. And then going back to the wavelengths, I was trying to match something similar, you know, to this curve here, the purple one. So I chose 2 white LEDs. I chose the warmer one, which is going to be this curve here, gives sort of this similar bell curve. And then I also chose the royal blue and the red just to expand out the blue wavelengths and to get a little bit higher on the red wavelengths. So it should give a nice mix of a full spectrum for the plants to grow. This is the heating. As you can see, there's not much concern for the blues. The light output is going to be in lumens. It's going to stay fairly consistent depending on how hot the junction gets. So this is up to 150 degrees C. The red, however, drops down rather quickly. So therefore I needed this heat sink that would dissipate quite a bit. This is some tests that I had done on the LED array itself. So, you know, all the way up at the junction, you know, I can't measure the junction, so we can only measure that starboard that the LEDs are on. But 50 to 70 degrees C puts us way over here, so hopefully I won't be losing a lot of light on that. Even if it does get all the way up into the 90s, it's just difficult with red, so you're going to lose a lot of light output. This is some comparison to some other light sources. So an industrial system would be using these high pressure sodiums and metal halides, which is difficult to see, but it says about 50 to 140 lumens per watt. And then this is for, I didn't put them all up, but this is for the white. I'll be running at 750 milliamps, which gives me roughly 170 to 200 lumens. So a lot less energy for more lumens. Power concerns, I chose this one. This is a 24 volt, 5 amp power supply. The idea behind that being that I want to be able to power all these devices that are attached to the board. The step downs were fairly easy to do just with these, the LM 7805 and 7812. We've been learning about those in class, so there will have some modifications in the programming due to the constraints of the chip itself. It can only give me an amp out, so one pump at a time will be running. And then the buck converter here will give me my constant current out to the LED arrays, and that will actually give me the proper voltage so that we won't overrun any of the LEDs. Here's some calculations for power. Originally when I did these calculations, I was planning on all the pumps potentially being on at one time. That's since changed due to the converters that I'm using. So these numbers are a bit high, but that's where I chose the 5 amp supply. It was a standard supply, it's fairly cheap. And if I want to, I can expand this system with that power supply. These chips were obviously an easy onboard fix, and that buck can, here's the ratings for that. It can give up to 32 volts out. We saw the forward voltage on the LED array was only around 17 volts, so we won't be exceeding that at any point. And then this is for the LM 7812. We only get an amp out of that, so that's why we won't be able to run all 3 pumps all at the same time. This is schematic layout. So I have my powers over here. This is power in. The 2 chip converters. This one's a step down to 5 volts, down to 12 volts, and then straight from the 24 volt supply is going to go into the buck pucks here. We have some N-channel switches that were chosen to be able to be used by your microcontroller. And then these are the motors, the power to the motors, and then the sensors are all over here, and I only needed one of the sets of pins from the microcontroller. This is the board layout. I tried to keep things somewhat in the same place. It was rather difficult to fit everything on to the board and get it to route 100%. I was finally able to get it to route 100%. So basically I tried to keep pump powers here. This is the main power in. The 12 volt converter step down for the pumps over here. And then straight from the 24 volts is going to come over. We got the 2 buck pucks here that are going to have to hang off the board. So that was the reasoning behind that choice. The screw terminals out to the LEDs. And then I'm going to use those little servo 3-pin things that we did on some of our other projects for the sensors. And then the board connector is in the middle there. This was the pin assignments. So if you remember from our A to D converters, these were basically the choices. So that was the first concern with assigning pins. Fortunately, it was all on that same block where the power and was, so I didn't have to use the two sides of the board. It was only one side that was needed. The LED arrays and the water pumps were just general purpose pins, so I could assign those just about anywhere I wanted, but these were the ones of concern. So basically I just went straight up. I needed 9 of them. We have access of 12, so I basically just used whatever ones I could find. These are going to be the switches for LEDs and the pumps. An N-channel MOSFET was chosen that was well within operating. The on voltage for the MOSFET needed to be well within the output from the micro, which is only 3.3 volts. And looking at the gate threshold on here, we see it goes from 1 to 2.5. So should have no problem turning that on. Putting it onto the curve tracer in the other room. They all seem to function very well. We also have pull down resistor here just to not let any sort of signals accidentally turn any pumps on, because we do have some power constraints on the chips and we don't want to blow that LM 7812. So this assures that it's not going to accidentally turn on by accident and only turn on when I want it to. This is a general layout of the programming. So basically I need some functions for timing, some assurance that the pumps are only going to come on one at a time, define lengths of time for the LEDs, and checks the sensors, and help maintain a moisture content, because I'd like this to run when I'm not at home. So basically this is going to set it up for, right now I have it as 18 hours on, 6 hours off for the lights. And then it's going to check all the moisture sensors. There'll be 3 in each row, so if any one of them goes low, it's going to turn that whole row on. And then here it's going to be checking the moisture percentage against a set number, turn it on for 5 minutes, and then it's got an additional 10-second wait, which might seem a little excessive, but in the scheme of looking at a whole day, an extra 10 seconds isn't a big deal to make sure that those pumps don't come on at the same time. And then down here there's a loop that waits an hour at a time. That's based off the 1 millisecond systic and 3,600 seconds in an hour. This was the setup for the A to D converter. So I wanted it as a 12-bit converter. So that's where this function that we've been using before was. I set up a little thing to measure the percent of moisture. So I picked a number that was a bit below the lowest value that I got, and range all the way up to dry. Basically, this is going to find the percentage of dry and then subtract that from 100 to get the moisture percentage, and then a little function to help determine this in the program. And then we have ethical concerns. It's low power. You got 2 12-watt LED arrays opposed to your typical 400 to 1,000 watt traditional high-intensity grow bulbs. You can use some fluorescence, which will still be higher, but typically if you're trying to, at least on an industrial scale, they tend to use these high-intensity bulbs. Less on time with the pumps. Hopefully they won't be on continuously, and only turn on if they get too dried out. So this is a little bit different than the traditional continuous flow where the pumps are just constantly cycling water through these plants. And, another thing is you'll know and you can decide whether you want to use pesticides. They may or may not need to be used depending on where you're using this. But opposed to many conventional vegetables that you get in the store, many of them are sprayed with pesticides that many people do not want in their bodies. And then also the choice to go fully organic if you want to or not. Both these can be chosen by the user, so that puts a nice choice given to them. And then of course there's price, satisfaction, and health. It's satisfying to grow your own plants. You'll have your own food. Hopefully it'll be producing more than you can eat. You could give that to people or donate it to people that may need it. Also having plants in your house is going to naturally clean your air. So hopefully you'll have cleaner air in your house and keep the cost down for your budget if you spend a lot of money on fresh fruits and vegetables. That was my presentation. If anybody has any questions?
Are you making this for other people or just for yourself?
Right now, just for myself, but I do have 2 friends that want me to build one for them.
I'm sure you charge enough. Go back to the page where you talked about, the slide where you talked about only one pump at a time. I think it was the first power slide. Did you say how much a pump takes, how much current it takes?
The pumps take 400 milliamps.
Okay.
That was stated on the water slide
Okay.
back at the beginning.
And that's the reason, like, so had you considered just putting 2 regulators in, or?
I have. After I thought about it, right now, board space is primary concern. It was pretty tough to get everything on that board as it was. I guess there's always the choice to make a second board and or use one of those little chips that we found from before. Again, the issue is real estate on the board itself is precious. But yeah, 12 volt, 0.4 amps.
And on your ethical concerns slide, I think those are great. It's the second to last slide. You mentioned one about, what pesticides are on. This doesn't deal with pesticides, this system.
Right. It would be something that the user could use themselves if they need to. Ideally, hopefully you don't have a lot of pests in your house, and so you may be able to control it yourself.
All right, I guess what I'm trying to ask is, there's really nothing in your project that lends
No.
itself to that particular point. Everything else, I think.
Well, ideally, we wouldn't have to be using that at all, so that was my reasoning behind that, is almost every vegetable you're going to get in the store is going to have some sort of pesticides on it. Even if they wash it, they'll still be residual. This eliminates that completely.
Yeah. Okay. Anybody have any other questions? All right, thank you.